All right, so this is our homework from last night, and I would like to give you guys the answers so you can check your work. If by chance you were absent, do I have any absent people in here who didn't get the worksheet from yesterday? Okay, um, so if by chance you didn't do the homework last night or you were struggling with it, still you should write down the answers, and then over the weekend get yourself caught up, hiding the answers. That way you then can try and see if you've done it right. So Charles' Law was our only homework last night, and we're going to get to the combined gas law later at the end of this period. Yeah, you shouldn't have. I wanted you to wait. That, in fact, is going to be Monday night's homework. This whole worksheet will be due on Tuesday. All right? So, answers. We've got 310 milliliters, 880 K, or 610 degrees Celsius. We've got 98 milliliters. Now, if you notice on problem 3, it has that weird line above the 5 or the 0. Apparently, that is another way to signify sig figs. Yeah, so 150 is 2 sig figs. 50 is actually 2 sig figs because it's telling you that 0 is, in fact, significant. This one is 50 milliliters, 2.3 liters. This one's 180 K or negative 93 degrees Celsius. Then you have 5.3 liters. And last you got, 331 K, or if you converted it back to Celsius, it's 58 degrees Celsius. Questions? Yes.
Number 2 is 884 K.
884 K. Yeah. So 884 rounded to 2 sig figs would be 880. And the reason why it's 2 sig figs is because when you add 273 that's not 273. When you add 273.15 to 40, what you get is 2 sig figs. Gosh, there's not much room on here. Let me write a little bit smaller here. So if I added 273.15 to 40 degrees Celsius to convert it to K, if you notice, the least significant place is the tens place, right? The 40 is ambiguous. So what I do is I do my little dotted line right here. And this would be 313.15. But what I do is I underline the significant place and I don't round yet. So that number is 2 sig figs, 2.3 liters is 2 sig figs, and 6.5 is 2 sig figs. That's why. Brian, your question?
Where did you get 273.15?
Because at the top, it reminds you that all degrees Celsius must be converted to Kelvin.
Wait,
and in fact, this, folks, go ahead and fix that. It should be 0.15. If you did all of your homework and did the conversions with just 273, you probably still be fine.
I thought that was just if you had to convert it, not if it was supposed to. It didn't say that.
You have to convert all temperatures to Kelvin. Yeah. So remember, that's why we're learning. Remember right here, yesterday on our notes, right here in red, it says temperature and gas laws must be converted to Kelvin. So maybe you missed that. I mean, I said it, I wrote it, but that doesn't mean you heard it, right? That happens when you're taking notes. Sometimes you don't actually process something. So now you know.
That was for something else.
That is for all of Charles' Law. Anytime temperature is involved, and you're about to put a temperature into any one of these gas laws. Now, Boyle's law doesn't even involve temperature, so I mean, there's no worry there. But Charles' law, the Lussac law, which we're going to learn later, and combined gas law, all involve temperature. The chit chat, by the way, is being recorded, so everybody's hearing how loud you're being. Those of you who have little chit chat side conversations. Question? Yeah. Can I do one? Yes, absolutely. Which one would you like me to do? Do you have a request?
The last one.
All right, let's do the last one. Why not? It's a good one. We're going to do number 8. A sample of argon gas is cooled, and its volume went from 380 mils to 250 mils. So right away, we see that this is the volume 1, volume 2. How did I know it was volume? Milliliters, good. Those units tell me it's milliliters. If its final temperature was negative 55 degrees Celsius, so is that T1 or T2? T2, because it said the final temperature. So this is T2. So let's go ahead and add the 273.15, or combine it, I guess. So 270, can somebody do that math real quick? What is it? What is it? 218. Can I get a second on that math? Yeah? Somebody else? Yep, okay. And then this is K. The significant figure would be this ones place right here because we put our dotted line. So that's our T2. How did I get to what? I took 273.15 and I subtracted 55 because it's a negative 55. Yeah. Remember when you combine negatives and positives, remember those rules. And it says, what was its original temperature? So what we're wondering here is what is T1? All right, so we've got our equation, V1 over T1 equals V2 over T2. We simply now need to just plug it in. I'm going to use this space right down here because I can. All right, so volume 1, we have 380 milliliters. And T1 is what I'm looking for. Volume 2 is 250 milliliters. Oh, this one's marked. And our T2 was 218.15K. There we go.
380.
Yeah, there we go. So 380, all three are significant. 250, all three are significant. And then the temperature, 3 of the 5 are significant. All right, yes. Yeah. This is a little bit tricky. The variable is in the denominator, so we're going to cross multiply. Remember that trick where you multiply those, which equals the multiplication of those. So we're going to say T1 times 250 milliliters is equal to 380 milliliters times 218.15K. Notice I'm careless with the order. You notice that? Like I put temperature first and then volume first. Why can I do that? Because of the commutative property of multiplication. Doesn't matter what order I do it in. Now I'm going to get the T by itself by dividing both sides by 250 milliliters. And before I do any math, I just confirm that everything cancels here. On the right-hand side, my milliliters cancel. I'll get to your question, Brian. I'm left in units of K. K is what type of unit? temperature. Good. And I go, all right, that's what I'm actually looking for. And then you do the math. And you just take 380 times 218.15 divided by 250. And you should get 331. Is that what happened? You forgot to divide? You get that. Question?
So it's isn't that supposed to be reversed? Or you're supposed to get V1 times T2 equaling V2 times T1. So I'm getting confused with what's V1 and what's V2.
So here's T1, here's V2. Here's V2, here's T1. Wait. T2, yeah. Sorry, now I'm confusing you. Hold on. Okay, so this is V1, and this is T2. Yeah, you're right, Brian. Yeah, we plugged it in, right? Did I do something wrong there? No?
I'm so confused.
And you're right, this is really quite confusing. You have to just slow down and make sure that you are substituting the correct values into the right places. Because honestly, it's very easy to make silly mistakes.
Wait, how did you get
Yeah.
to the first place at this problem?
Well, let me finish this one.
Oh, it's right.
All right, so now, before I'm done, I have to look at sig figs. So I have 3 sig figs here, 3 sig figs here. 3 sig figs here, and 3 sig figs here. Therefore, my answer must be 1, 2 to this place, 3. I look at the 5. Oh, and the answer, in fact, is 332K, not 331K. So our answer key was wrong. Maybe it's because they used the rounded 273. It may have made a difference. Jojo?
What if you put 218 instead of 218.5?
Yeah, and I bet you your answer would have come up as 331. Yeah.
It would have come like 360.
Okay. Okay, that's probably why. Yeah. So, welcome to chemistry. Different things have different rounding. 273 is just rounded. 273.15 is just more precise. Okay. I am really being a stickler about doing the 0.15 because I know for sure one of the test questions I'm giving you is going to involve it. So I want to prepare you for it and not catch you off guard. So, wait. Somebody said wait. Are you wanting to see? Aiden, actually, in the previous video that I posted yesterday, I show problem 1. So if you could maybe review, you just kind of scroll to the end of it, or, fast forward to the end of it, not scroll, but, scrub. I don't know, is that what it's called when you move it on a video? Get to the end, and then problem 1 is shown, and hopefully that will help you as well. Yeah. The third one, yeah.
Wait, you do question 7?
I need to move on to show you other gas laws. So if we have time, I'll come back to 3. Maybe I can come back to 7. So what I'd like to do right now is ask that you get out your notes that look like this from yesterday. We're going to talk about the second to last gas law called Lussac. This is actually misspelled. This is an A. It's pronounced like guy, but it's spelled like gay. It's a French name. So in English, G-A-Y, we pronounce gay, and in French, we pronounce it guy. So there's actually misspelling. So Gay-Lussac's law is the relationship between pressure and temperature. So let's identify for ourselves what is being held constant. Volume. Volume is being held constant. Tell us the other one. Sorry. What's the other one, though? There's a second one. If you don't know it, flip over. Particles. Good. Yeah, number of particles. Will you let them? Oh, no, maybe they're. I don't know. All right. I'd like to remind you of the lab that we did with the tiny little test tube, and we chilled the test tube in ice cold water. And then what we did is we put the dime on top of it. So we did not change the volume. We also sealed it, right? We got it kind of wet and we put the dime on top and we sealed the test tube. So that's why the number of particles are not changing. And then we warmed it up. So if temperature is increased, what happens to the pressure? What happened in that experiment? We warmed up the test tube, and what happened to the pressure? It increased. Yeah, and that's why the dime started doing the little jump thing, or maybe it like burped a little bit. All right, so if temperature increases, then pressure increases. And vice versa, right? If we decreased the temperature, we would be decreasing that kinetic energy. All the little particles would be going much slower, and then we would also in turn cause the pressure to decline. So if one goes down, the other goes down. If one goes up, the other goes up. We call this type of relationship, what type? What do we call it? What type of relationship is this? Look on yesterday's. We had another one that was similar. What type of relationship? Inverse or direct? Direct. Direct. This is the direct relationship. We saw this yesterday with Charles' law. Yeah? Yes, folks in the back there? Let's refocus. Thank you. A direct relationship. All right. If I were to graph this, the little trend line, we would have temperature and pressure, and this would be a linear graph, meaning it's a line, and it would increase. So now let's do our little picture of the beakers. What's going on with the temperature? It's going from 100 to 200 to 300 to 400, right? It's doubling, it's tripling, it's quadrupling. So if this is our temperature one, and let's pretend like our pressure, which by the way, it's kind of weird that this is a picture of a beaker because it's a measurement of pressure, but we're just going to roll with it. So the pressure one would in fact be 20 millimeters mercury. So if I doubled my temperature, what am I going to do to my pressure? Double it. Good. So it'll go up. It'll be 40. All right, so if I tripled it, you guessed it, it would triple the pressure. So that would be 60. And then finally, if I quadruple it, I would quadruple my pressure. Now in chemistry, it's typically not as pretty as, hey, it's a multiple of 2 or 3, right? You're not doubling or tripling or quadrupling often. You'll see the relationship is like, oh, you increased it by a factor of 1.72. Right? So the other one should increase by a factor of 1.72. So it's often weird numbers, not nice, clean numbers. Look at the trend here, too. Yeah, Brian?
Well, I think it's picking up from yesterday when we were doing our work.
Yeah?
I think we figured out why we didn't really get it. It was because we already did something by photon and we didn't actually convert
Oh yeah, you're right. It was already in Kelvin. So if it's given to you in degrees Celsius, you got to do that Kelvin conversion. Yeah. All right, so you notice here this is like a linear equation, even though I drew a subtly crooked line, but you get the gist. It increases. All right, so we now have seen three types of relationships. One with volume pressure, right, Boyle's law. One with volume temperature, that's Charles' law. And now with pressure temperature, that's Lussac's law. The final law, go scroll down and see how they have a little empty space here on your bottom left-hand corner. I'd like to show you, oops, not a highlighter, what the combined gas law is. The combined gas law literally is just that. It combines all three laws together. So it's P1 times V1 divided by T1, P2, V2 over T2. And I want to show you, if we were looking at this gas law, do you guys see, I'll point out what Boyle's law is. Boyle's law is the pressure-volume relationship. Let's make Charles be green. Charles' law compared volume with temperature. And then Lusac's law, we'll make him be purple, was just pressure. Oops. Pressure compared to temperature. So do you guys see how this particular gas law combines them all together? So we see things like this all the time. Trying to think of a good one. It's even hard to think about because often what we see out in nature is particles change too. But imagine if we were in this room and no, that wouldn't work either. Combined gas laws are things like maybe tire pressure, right? So as the temperature increases, right now the temperature is decreased, therefore decreasing pressure, and what happens is our volume changes. So let's go ahead and, rather than just think about this, let's do some practice problems. So flip over the back side of your homework. Oops. There we go. All right. Combined gas law. I'd also like you to get out a piece of paper as well. So you're going to have your homework out, your notes out, and a piece of binder paper out. You should have 3 pieces of paper on your desk, right here. And your phone, I should have used those. Phones are put away. All right. When you're looking at the combined gas law, how many variables are in the combined gas law? 3, but then there's different versions. So really, how many is there? 6. Good. In these problems, they're going to give you 1 less, right? So if there's 6 variables, the problems will give you 5, and you're asked to solve for the 1. If they give you only 4, you can't solve it. It's unsolvable. Right? So if you have 6 variables, you have to have at least 5 in order to solve. If you look at, for example, Boyle's law right here, there are 4 variables. So they must give you 3 of them in order for you to solve. So if you look at the back side of last night's homework, there are 6 variables. Do you see problem 1? They've given you 5. You got to solve for the 6th. Right? Problem 2, they've given you 5, you got to solve for the 6. They're always going to give you 5 and ask you to solve for the 1. Does anyone see what's going on with temperature? What's wrong with it? It's in Celsius. So to do problem 1, let's go ahead and convert our temperatures. So this is 293. And that's the significant place. Why? Because 20 dictates what's the least precise decimal. And the unit is K. And let's go ahead and convert this one as well. 273.15. So that's 303.15. So on your separate sheet of paper, let's go ahead and solve our very first combined gas law problem. You just add 273 to those temperatures. I just converted it. So let's go ahead and write our combined gas law. This is on your binder paper. And let's go ahead and start plugging in our values. P1 is 1.5 ATM. V1 is 3.0 liters. T1, we're going to put the value in Kelvin. So that's 293.15 Kelvin equals, so I plug in P2, which is 2.5 ATM. V2 is what we're looking for, divided by that converted temperature, which is 303.15 Kelvin. I just like to have parentheses around everything. It makes it nice and clean. Is there any questions on how I plug this in? All right. Anybody know the trick for how to get that V2 by itself in one fell swoop? Just a one step? Maybe? Cal, you want to take a shot at it? Multiply by what? Yeah. Multiply by those numbers, but you flip them, right? You multiply by the reciprocal. And what you do to one side, I'll do it in blue. So if I multiply by the reciprocal, that gets the V2 by itself. Notice I'm being really meticulous about using all my units. When you're doing combined gas law, it becomes really important because you can just kind of lose track of everything if you don't. And before I do all that math, I need to make sure everything is set up correctly. My 2.5s cancel, my ATMs cancel, 303.15 cancels, my K's cancel. I am left with V2, so I'm looking for volume. On the left-hand side, I look at my units and make sure, Alex, it's all set up, right? So my K's cancel, my ATMs cancel, and I'm left in units of liters. ATM over ATM. One's in the numerator, one's in the denominator. Units cancel just like numbers. ATM is in the numerator, ATM in the denominator, they cancel out. Yep, the K, one is in the numerator, one's in the denominator. So remember, it's like, a number divided by itself. Well, it's a unit divided by itself. So those just turn into 1, or they cancel. And I'm left in units of liters. Liters are a unit of volume. So that means I've set this up correctly. Yeah. And believe me, as you start to do this and your units don't cancel, that's where you stop right then and there and go, wait a minute, what did I do? I messed something up. Maybe I plugged something in wrong. All right, so then you take your calculator. Hey folks, this is where it gets a little tricky. You need to know how to use your calculator correctly. And I'm not being sarcastic with how to use it multiplying and dividing. If you plug in 303.15 times 1.5 times 3, then you hit divided by, you either need to do parentheses in your calculator to multiply those two, or what I like to do is just hit divide by 2.5 and divide by 293.15. So could I please get you to calculate that right now? If you've got a phone in your hand or a calculator in your hand, please calculate that. Brian, what'd you get?
Wait, no, I'm getting confused with what you're asking.
Oh, do the math. What'd you get? 1 point.
My question is, cancel K.
1.861. What did you say? Because there's a K right here and a K right here. One in the numerator, one in the denominator. One ATM in the numerator, one in the denominator. So they cancel. Yeah, does that make sense? How one's in the top, one's in the bottom? Yeah? 1.861. Okay, we got a second on that. So let's go ahead and do our sig figs. Yeah, be careful. If you hit divide and then times 293, what you're telling the calculator is you're taking the answer and multiplying it by 293. That's not what you're doing. 293 is supposed to stay in the bottom. So you need to use parentheses, or you hit divide twice.
Well, wait, I did it. I just times divide 2.5 and divide 293.
Yeah, that's what I do too. You hit divide by 2.5, divide by 293. It's faster, I think. Adrian? So you take 303.15 and you're going to hit the button multiply, right? I just want to show you the calculator function. Then you hit multiply. Then you hit divide. And then you hit divide again. So this is the calculator function, right? This is the buttons you push. All right, let's look at sig figs here. So we've got 303.15, and I have identified that 1, 2, 3 sig figs are here. 1.5 ATM. How many sig figs do we have there? We've got 1, 2. 3.0. Remember, this 0 is to the right of the decimal, and it ends the number. So that would be 2 sig figs. We count them both. We got 1, 2. And then here is 1, 2, and then we've indicated that there's 3 sig figs. So what are we going to round our number to? We've got 3, 2, 2, 2, and 3. We're going to round it to 2 sig figs. 2 sig figs, which is 1.9. So we go 1, 2 sig figs. I look at the 6. So it's 1.9. Am I done? What am I missing? In liters. Good. Why didn't I use what? 303.15? No. Yeah, I did. Right here. 303.15 times 1.5 times 3.0 divided by 2.5 divided by 293.15. Yeah? What I'd like you to do to report your answers is on the worksheet, go ahead and write your answers in the box. That way On Tuesday, when we go over it, we can check our work quickly, but please show all your work like this. That's why you need a piece of binder paper to show all of it. Now, I'd like to do number 3, because we got 4 minutes. I'm just going to crank through it. All right? Number 4, it's a little bit different. Yes, you are. And you're going to turn it in on Tuesday. Let's look at number 4. Sorry. 1, 2, 3. Nope. Nope, let's look at number 3. Yep. All right. So number 3, we're going to need to convert this temperature to 295.15 Kelvin. And everything else looks pretty good. So let's go ahead and plug that in to our P1, V1 over T1, P2, V2 over T2. Is it worth it to write this every single time? The answer to that is yes, because you do have to memorize these equations. So the more you write them, the more they'll be in your brain. All right, so pressure 1 is 600 millimeters mercury.
Wait, shouldn't that be T2?
Yep, good looking out. Volume 1 is 2.5 liters. Thanks, Brian. Good catch. Our temperature is it 295.15? Did I just do that math right? Okay, thanks, because I'm doing that from memory there. Our P2 is 760 millimeters mercury. Our V2 is 1.8 liters, and now we're looking for T2. The reason why I feel like this is a bit tricky is this is multi-stepped. Remember how you cross multiply? All right, so let's do it. T2. So I just watch and not write, because this is going to be on a video and you can write it later. Okay? Just watch how I do this one. So 600 millimeters mercury, because I can write pretty fast, if you haven't noticed. And then the other side would be 295.15 K times 760 millimeters mercury times 1.8. Now I have to get T2 by itself. So do you see how when the denominator is the unknown, got to do this extra math step? All right, so we've got that. These cancel, and then I check my units. You guys get the idea? I wanted to show you that extra step. All right, folks, have a great weekend.